Hello and welcome to this lecture number 2 of week 5 of the course on control engineering. So in the previous week lectures we had defined types of a system, and we also saw how different types of system uh, responded to different inputs or even reference signals. So type largely was defined by the number of poles at the origin. A type 0 system had no poles at the origin, type 1 system had one pole at the origin, and so on. And we were interested in, and there was a direct relation between the type of the system and the steady state error, which we will call as ESS. So for a type 0 system, if I have a step input, so type 0 system will track a step input with some error, an error defined largely by this KP. And a type 0 system cannot track a ramp input, and a type 0 system cannot track a parabolic input. So this is not possible. Type 1 system perfectly tracks step, so there is no steady state error. So this was, these are the numbers which have the steady state error. And a type 1 system tracks a ramp with some constant error, and this error is 1 over kv, where kv we defined it as the velocity error constant. And similarly, a type 1 system is unable to track a parabolic input. And you go higher and higher. A type 2 system can, of course, track a step input with zero steady state error. It can track a ramp input with zero steady state error. And it can track a parabolic input with some constant error. And you see, as the type increases, the ability of the system to track higher order reference or input signals increases. So the motivation is, and one of the largely used controllers is PID controllers to industry, to academia, and so many other applications which we will find. So this forms the fundamental backbone of any control design. So largely we will see, and we will kind of summarize this again at the end to see that I have a proportional component, and the reason I call this proportional derivative and integral is each of these components you can see here. 1 over s adds and acts as an integral term, and multiplication with s serves as a derivative term. So this a controller continuously calculates the error between the desired and the actual output, and adjusting the control law to minimize this error. So we'll see how proportional, integral, and derivative terms, each of these contribute to the overall control action. What are we interested in? We are interested largely in a transient design, where we were interested in the overshoot and the settling time. This was largely related to the damping and the omega n. So the physical properties of the system. And in the steady state, we were interested in a steady state error, and this largely had to do with the type of the system. We also saw several examples and plots of how different systems react to different kinds of inputs and also disturbances. So when we talk of control design, we also talk of ability to reject disturbances that we saw in the regulation problem. Okay, so let's say what happens when I add an extra element. So I have a certain plant, and we know how a standard second order system responds. So you have a overshoot, a settling time, and so on. And this is usually for an underdamped systems. Okay, so let's stick to underdamped systems and see what happens when I add a zero. And say I had a zero at minus zeta omega n with an alpha. I can choose this alpha. Okay, and the reason I kind of do it is largely because I want to maintain the DC gain of the controller at one. Without any loss of generality, I can do this. Okay, so if I have I call this as uh, G1S, where I have the original G without a zero. And now I have the total G1 is now I can add the sum of this plus this. Okay, no, this is nothing special here. And if I say the step response or the unit step response of the system will have two components. One is the component which will be decided by the original plant without any zero. And now I have this. Okay, so I'm just a little messing something. Okay, so G1 S by S. So this will have two components. One is the step response of G, and then this term. So okay, I think I'm just little I made errors with some notations here. Okay, let's write down this properly. Okay, so this will simply be G of S, right? So no GS. Okay, so GS of S, this will decide the step response of the first term. Again, linear systems, so superposition and all. And the second term, again, 1 over S with everything over here. So that is 1 over S with everything inside the plant. So now I have, so this is my original output. If I call it as Y1S, that is the response of G. Okay, I think this should be Y of S. There should be no subscripts here. Okay, so this is the original response. And now to this, I add the response of these, the additional term because of the zero. Okay, now I have Y of S and I have S times Y of S. And this we know, this corresponds to a derivative effect. So if I go back and take the Laplace inverse, so Y1 of t is the original response plus the response of the derivative with some constants, and these constants we can choose. Right? We'll see what happens if alpha is small till alpha is large. What we just saw was adding a zero will have the original output plus the derivative of the output with some constant here, and the constant is largely depending on the location of the zero. Okay, so as always, we'll just look at some plots and say what happens for very large values of alpha. Large values of alpha essentially means that this will be the zero is very far, or this term will kind of go to zero, or the zero does not exist. So the natural response of the system without the zero will be somewhere close to here. Okay, but for alpha equal to 0.5, what you see now is so my natural response is somewhere close to alpha equal to zero. For alpha equal to 0.5, I see a very large overshoot. Then I have for alpha equal to 1, a different kind of overshoot. And as alpha goes to 100, I see that, okay, I recover my original response, which will have some kind of a tolerable overshoot, about 15 to 16%. For different values of zeta, I can for different values of zeta, I still see that the overshoot is much larger for smaller alphas, and as alpha goes larger, we are closer to the original response of the system. So if alpha is large, the zero will be far from the poles, and the zero will have less effect on the response. So if I just draw on the complex plane, say suppose here are my poles, alpha goes very, sorry, here are my poles, alpha goes very large, say my zero is somewhere here. This has kind of no effect on the system response, or very less effect on the system response. Okay, so what do I observe from here? If I just add a zero, it resulted in an increased overshoot. What happens in the C? All these blue, all these lines which correspond to alpha equal to 0.5, or curves which correspond from alpha equal to 0.5 till 100, they kind of settle down again at somewhere very close to each other, right? So even though I see different kinds of overshoots, there is no significance in one. There is no much significant difference in the settling time, and also in the steady state error. Right? So in the steady state, there is very less effect of it. But what I can see is for smaller alphas, the response is faster. You see this system moves slower here when alpha equal to 100, or even when alpha equal to say 6, for example. Whereas when alpha equal to 0.5, the system moves much faster. So I have an increased overshoot, or I have a faster response, but an increased overshoot. And of course, as alpha goes to infinity, the contribution of the zero to the system response decreases, and we recover the original system behavior. Okay, I do the same thing, and I see what happens uh, when I just add an extra pole to a second order system. So this is how my second order system looks like. I just add an extra pole at s equal to minus. Okay, so again, as alpha, so maybe somewhere here are my poles, and here is the zero. And as alpha goes to, we'll see what happens for smaller values of alpha. So my original response is somewhere here. It's hidden somewhere here in this thing, the thick blue curve. Okay, this is my original response. This is when alpha is 0.5. You see, there is a lot of, which means sorry, I'm just looking at poles only, right? Which means that my closed loop pole or my additional pole is somewhere close or to the original poles. Alpha equal to 0.5, you see a lot of change in the response. Alpha equal to 10, which is again this purple line here. Okay, alpha equal to 0.5, you see a different response. Alpha equal to 1, I see a much different response. Of course, the system which earlier had an overshoot is now behaving like an overdamped system. But however, after a certain value of alpha, I see that the behavior doesn't change much. Okay, so for alpha equal to 10, the response of the system with and without the pole are similar, and for the similar for any other alpha which is greater than 100. And as alpha goes further and further, we recover the original response. So the original poles for this system are at, so I'm just looking at a system of the form s square plus s plus 1. Okay, so these are the original poles for alpha equal to 10 and greater, the original poles are dominant. So even though this pole is present or not, the response is pretty much similar. The overshoot doesn't change much. All these three lines, which are the original one, alpha equal to 10 and alpha equal to 100, the overshoot changes by a very small margin, right? So I can still say that my system, my original system behavior with these poles is the same as with this additional pole. And therefore, I say that this pole pair largely decides how the system behaves. Alpha equal to 10 or 100 doesn't really have much effect. And poles like these are called the dominant poles, as they decide how the system responds. So largely that, okay, so this, it is also because these poles are much further away from the original poles. So these poles which are closer to origin are called the dominant poles. And later in the course, we'll just largely see how just a dominant pole analysis reduces my order of the system to a second order system, and I can largely ignore the presence of other poles. We'll also quantify what is a dominant pole and so on. Okay, so that brings us to the first control laws that we will talk about, namely the proportional controller. As the name says, I just have the controller is just a gain, which I can increase, say greater than or equal to 0. As usual, my error signal sits here. I want the error to go to 0 for a tracking or a regulation problem. And in case of a regulation problem, I want my disturbance also to, the effect of disturbance also to go to 0, or in such a way that the disturbance does not contribute to the error in the steady state. Okay, let's talk with the first order system, where this g of s is now 1 over ts plus 1, and here I just have a k. Okay, so what will happen here is e of s, which we saw was 1 over 1 plus L. So E of S will now just be, okay, all this should be Kp, Kp. We do all the math and I just get that E of S is 1 over Kp plus 1. Okay, when Kp equal to 0, okay, I have error of 1 because nothing really, the system doesn't produce any output. So what is the change now? So we talked about time constants of the system. The original time constant was T, and with the introduction of the proportional controller, my time constant now changes from T to T over 1 plus K. Okay, so there's an improvement in the time constant. There is also a non-zero steady state error. A non-zero steady state error which can be which can be reduced by choosing a large k. So my steady state error 1 over kp plus 1, and you see as kp increases, the steady state error decreases. Again, I'm talking of a step response. But of course, we'll see in some other systems that choosing a large scale may not really be useful for us, that it can destabilize the system. Okay, a quick question that we will answer here is what happens when the plant is of the form js square, and so we'll write here. So this plant is no longer ts plus 1, but it is now just j of s square. The controller remains the same. This is 1 over js square. Okay, so what is the closed loop? The closed loop transfer function now is p g times gc over 1 plus g times gc. So what is g? G is 1 over js square. Controller is kp over 1 plus js square. Sorry, 1 plus kp over js square. Okay, so where are the poles of the closed loop? So where are poles of g of s? That is at 0, 0, and this we know is unstable. Okay, so where are the poles of the closed loop system? Look at the denominator. The denominator now here is, I'm looking at js square plus kp equal to 0, or s square is negative of kp over j, and s is now plus minus j kp over j. So the roots are imaginary, and if I keep on increasing, so my open loop poles were here. If I keep on increasing if I keep on increasing the gain, the poles just move on the imaginary axis. So when j is 1 over s square, we'll just have poles on the imaginary axis. Or at best, I can go to a marginally stable system. Okay, so to summarize, proportional control improves my time constant. Of course, there is a zero steady state error. Again, I'm looking here at a first order system, right? There is a non-zero steady state error which can be reduced by choosing a very large k. But we have to be careful that by adjusting the gain, we are not destabilizing the system. Okay, I'll just go now from first order to a second order system. Say I have G now of this form. This just keep in mind that this is a type 0 system, because I'm just having G of A over S square plus A1S plus A2, and then a KP and so on. Okay, so I'll just do the closed loop system. I look at the denominator of the closed loop transfer function, and I have a characteristic equation of this form now. Okay, so if I look at this So this term corresponds to 2 zeta omega n, and this term now corresponds to a2 plus kp times a is omega n square. So something changes only in the omega n square. And this constant term, this can be controlled by selecting kp, which determines the natural frequency. But through this controller, I am unable to control the damping term, which is independent of kp. That's also you will see here, right? So here my poles will just be, so my closed loop poles are just decided by 1 over js square plus kp, right, in this case. So proportional control does not contribute to damping. System which was oscillatory will still tend to remain oscillatory. Okay, so let us see with some plots of what happens with different levels of kp. If kp is made large, so you see kp equal to 1. So this is my reference. Kp is 1. Again, mind you that this is still a type 0 system. Okay, so type 0 system, step reference will have a steady state error. Okay, we'll see how this error changes, right? So for small value of kp, I have a much larger error. And if kp is made large, I am getting a smaller steady state error. Okay, of course, in this case, well, the damping may be too low for a satisfactory transient response with proportional control alone. So the reference input, and the reference was such that it had an initial slope of 30 degrees centigrade per second for a duration of 30 seconds, and then it had a steady state value, or the reference moved to a steady state value from a reference which was a ramp. It just became a constant reference. Okay, can we see if I can use a proportional controller that minimizes the tracking error and the steady state error? Okay, so the given plant is of this form. I have the controller which is of the form kp. The closed loop transfer function is now given by this, and I have a reference signal is such that it should go from 30t from 0 to 30 seconds and 300 for t greater than 30. Okay, now look at what is the type of the system. Type of the system is a type 0 system. The reference initially is a ramp. We go back to the table and ask ourselves what happens when the system is of type 0. The input is a ramp. Well, we are here, input is a ramp. It cannot track. So the steady state error will be infinity. So a type 0 system cannot track a ramp. So initially we might be in trouble here, and we'll see why we are in trouble with the help of some plots. We know because it's a type 0 system, the ramp will be with a steady state error of infinity. It cannot, type 0 system cannot track a ramp signal. Okay, what happens after that? After that, it just becomes a step. So I know that type 0 system can track a step with some steady state error. Okay, let's see first how the plots go, right? So for this is my reference, right? The one here in the dotted one. Okay, now for some value, small value of kp, you see that the distance between the reference and the blue line, this increases. This is my error. So the error increases. Okay, the error increases with time. And if I keep just, if I don't stop the ramp here, this will keep diverging from each other. This will go here, this will go here, and so on. Okay, however, good thing happens here is that the reference now changes to a step. Okay, and I know that type 0 system can track a unit step with some reference. So this is my steady state error. here for a certain gain, and it kind of keeps going down as I keep on increasing my gain. Okay, so I can also see here, right, the tracking error initially it keeps on increasing. This has to increase because my system cannot track my system cannot track what you call my system cannot track a RAM signal. But since it changes to a step here after 30, I see the little oscillations, and then the system settles down to some value with some steady state error. So here the error is about some 25 degrees. Here the error is much lesser, about 10 degrees, and it keeps on reducing as we increase the value of KP. Okay, so similarly, we also saw what happens to the steady state error due to a disturbance, right? So this is all those problems that we had done of 1 over s plus 2 and a 5, and so what was the effect of disturbance? Just replace a 5 with any other gain, and you will see that the error due to disturbance will also decrease as the gain KP is increased. But then, of course, there will have other effects of the system in terms of stability and so on. For larger order, and this we will see a little extensively in the next week's content, increasing the proportional gain can actually make the system unstable when the gain is high. For a type 0 system, the system with proportional control will have a non-zero steady state offset in response to a constant reference input. And also, it will not be able to continuously or completely reject a constant disturbance input. And we have been talking of this in the last 3 lectures or so. So one way to improve the steady state accuracy would be just go beyond proportional control. Okay, so what we saw here was there is some non-steady state offset, there is some steady state error. Okay, so can we say what do we do with steady state error? Can I say I can introduce an integral control? And recall those examples where we had 5 over s instead in the controller instead of just 5. What happened in that case? It had the capability to reject a step disturbance. Similarly, when the plant was js square, at best my proportional controller gave roots on the imaginary axis, so the poles were on imaginary axis. This is oscillatory response and also called as marginal stability. So we'll see going beyond proportional control will solve these two problems in terms of integral control and derivative control. So to summarize, we saw the effect of adding zeros, effect of adding poles. We motivated the basic controller, the proportional controller, listed its advantages and disadvantages. In the next lecture, we talk of integral and derivative control laws. Thanks for listening.